So as a very basic example, we've got 2 degrees of freedom, we've got 2 masses which are the same, and we've got 3 springs which are the same. There's no dampers, we don't worry about it. And we've got x1 and x2, and the question is, find the equation of motion, find the natural frequencies, and find the mode shapes. Well, it's very straightforward. The mass matrix is m and m in the diagonals and 0 everywhere else. For the stiffness matrix, okay, in the diagonals, let's take x1, okay. The first item in the diagonals will be the sum of the springs connecting mass 1, this one here, because this is x1, to ground or to another mass. So obviously quite clearly it's going to be 2k. Okay, and for the second diagonal, that's quite clearly also going to be 2k. And then for the off diagonals, so first column, second row, and second column, first row, it's going to be minus the sum of the springs connecting the masses to each other. So it's going to be minus k. And so quite clearly you can jump straight to that using the quick method. We make the substitution, okay, to end up with this form of the equation. And look, this term is multiplied by x1 and x2. This one's also x1 and x2. The cosine term can disappear. We can combine those 2 matrices together, and that will give us our mechanical impedance matrix. So that line we had on the bottom gives us our mechanical impedance matrix. You take the determinant of this, okay, so you end up with this as your solution. When you multiply this term by this term, minus this term by this term, you end up with this as your equation. M squared, lambda squared, okay, plus 4, minus 4 mk lambda, plus 3k squared. What I've done is I've replaced omega squared term by lambda. And you can end up finding that, if you go through the quadratic formula, you should all know the quadratic formula, yes? Minus b plus minus the square root of b squared minus 4ac over 2a. Okay, you just go through that process, you end up with, we've got 2 plus or minus 1 k upon m. And so if you go through that, you get 2 values, k upon m and 3k upon m. And obviously omega 1 will be the square root of the first term, and omega 2 will be the square root of the second term. It doesn't matter what order you do them in, okay? Just make sure you're consistent with the suffixes. Omega 1 will refer to the first mode, and omega 2 will refer to the second mode. Okay. So with the mode shapes, we replace x1 and x2 with 1 and r, okay? And then you stick in omega 1 to find r1, and you stick in omega 2 to find r2. It's quite straightforward. And so if we went through that process, for omega 1, okay, we had a m omega 1 squared. Well, if omega 1 is k upon m, then you can obviously replace that, and there you end up with k. And so we had a k, 2k here minus a k term. Obviously, what I've done is I've just divided the whole lot by k to get rid of the k's. We end up with 2 minus 1 times by the vector 1 and r1. And obviously, if you go through the process, you end up with 1 times by 1 minus r1 equals 0. So therefore, r1 must be 1. Okay, that makes sense. The masses are moving up and down together. For omega 2, so we stick in 3k upon m for omega 2 squared. Again, the m's will cancel. We end up with 3k. I divide the whole lot by k to get rid of the k's, and we end up with minus 1 times by 1 and r2. So you end up with minus 1 times by minus 1 minus r2 equals 0. Therefore, r2 must be minus 1. So those are the 2 mode shapes. We had 1 and 1. Okay, so the 2 masses are moving up and down together, okay, in unison. And then the second mode shape, they're moving in opposite directions, okay? When this one moves up by 1, this one will move down by 1, okay? Because those are the 2 mode shapes. And obviously this is a very simple case where the masses are the same and the springs are the same. You've got those 2 natural frequencies. Often that won't be the case, okay? You'll have different masses and different spring stiffnesses, and so you won't get exactly the same sort of motion. But this very simple case, that is what will happen. And the first natural frequency will be a certain value, and this will be 3 times, root 3 times that natural frequency will be the second value. And the general solution, like I said, basically is a superposition or the summation of the first mode and the second mode. Okay, and so we've got the first mass, we've got C1 times by cosine root k upon mt plus phi 1, okay, and plus C2 times by 1 times by cosine of root 3k upon t times phi 2, okay. And this, obviously with this one down here, you have to include the values that we found for r. And those terms C1, C2, phi 1 and phi 2 can be found from initial conditions.